Some black holes pack more mass than 1 billion suns into a region no larger than a city. They bend space like a heavy bowling ball on a trampoline and tug so hard that even light can't climb back out, which is why they're black. Forget the Hollywood vacuum cleaner myth. Most black holes sit quietly, and we spot them by the way they yank on nearby stars or light up when gas falls in. In the next few minutes you'll get simple, clear answers: how they form, what would actually happen if you fell toward one, why their ripples in space are a whole new way to listen to the universe, all explained with everyday examples like whirlpools, trampolines, and the occasional bowling joke. Stay with me and you'll be able to explain black holes at a party without sounding like a textbook, and maybe even win a bet. What is a black hole? A black hole is a place in space where gravity gets so strong that nothing nearby can get away, not even light. Gravity is the pull that keeps your feet on the ground and the moon circling Earth, but inside a black hole that pull becomes extreme. The edge of that region is called the event horizon. Cross it and there's no turning back. Think of it like a point of no return around a whirlpool. Far away you can steer clear, but once you pass the swirl's rim you get swept in. Most black holes form when a very massive star runs out of fuel and collapses under its own weight, squeezing a huge amount of matter into a very small space. Some are relatively small, in cosmic terms, containing a few times the mass of our Sun, while others sit at the centers of galaxies with masses millions or billions of times greater. The amount of mass packed into a small region means density and gravity become enormous. You can compare it to squeezing many cars into the space of a single shoebox, only far more extreme. Yes, it's dramatic, and no, you do not need to worry about your neighborhood suddenly turning into a black hole. Inside the event horizon all paths lead inward toward the center, where the mass is concentrated in what physicists call a singularity, a place where our current laws of physics stop giving clear answers. Surrounding many black holes is a brightly glowing ring of gas and dust called an accretion disk. Material spirals in, rubs against itself, heats up, and shines in 10th rays and light. Those bright signals are how astronomers spot black holes, not by seeing the hole itself, but by seeing its influence, a star orbiting something invisible, or gas glowing like embers as it falls in. There are also powerful jets that shoot away from some black holes, like cosmic garden hoses, and these help reveal the black hole's presence too. Black holes are often pictured as cosmic vacuum cleaners, but that is misleading. If our Sun were replaced by a black hole of the same mass, Earth would keep orbiting pretty much as it does now because the overall gravitational pull at our distance wouldn't change. You only get ripped apart by gravity, a process called spaghettification, if you come very close. So everyday life is safe from wandering black holes. In the larger picture, though, supermassive black holes help shape galaxies and act as engines driving spectacular cosmic fireworks, proving that even objects that eat light can have a very bright impact on the universe. How gravity warps space and time. Massive objects bend the space around them in a way that's easier to show than to say. Picture a stretched sheet and a heavy ball sitting in the middle, and you'll get the idea. Space and time are not separate stage and clock but a single flexible thing called spacetime, and when something with mass sits in spacetime it makes a dent. Smaller objects then move along the slopes of that dent, which looks to us like attraction. Planets orbit stars because they are rolling along the curved paths made by those dents. It is less like an invisible rope pulling and more like following a groove carved into the fabric beneath you. Light follows those same grooves. When a beam of light passes near a massive object its path bends a little, and that bending can bring light from a distant galaxy into our view even when the galaxy would otherwise be hidden. Telescopes sometimes see arcs or multiple copies of the same object in the sky because a massive foreground galaxy acts like a cosmic magnifying glass. That effect not only makes pretty images, it gives astronomers a practical tool to weigh galaxies and find stuff we couldn't detect any other way. Clocks behave oddly too, and this is not science fiction. The stronger the gravity, the slower time ticks compared with a location farther away. Precise clocks at different altitudes on Earth show tiny but real differences, and engineers must correct for this when they design the GPS system so your phone doesn't think you're in the next town. Pilots, satellites, and even experiments in tall buildings must account for the fact that, what time it is, depends on where you are in the curved spacetime around Earth. Near very compact objects, the warping becomes extreme. There is a boundary called the event horizon where the curvature is so steep that returning is impossible. To escape from within that boundary you would have to outrun light. Falling toward one can stretch and squeeze you because gravity at your feet can be much stronger than at your head, an effect colorfully nicknamed spaghettification. From far away an object approaching this boundary appears to slow and grow faint, which is a direct consequence of how time itself behaves in intense gravity. The warping of space and time isn't just a thought experiment, it makes measurable ripples. Collisions of massive bodies send waves through spacetime much like a boat makes waves on water, and observatories have picked up those vibrations. That strengthens the picture that gravity is geometry. Moving masses change the shape of spacetime and those changes travel outward as waves that we can detect. So whether you're thinking about why planets orbit, why light can bend into view, or why a clock in a satellite needs adjustment, it's all tied together by the simple, strange fact that mass reshapes the space and time around it. Event horizon, the point of no return. Around a black hole there is a boundary where gravity becomes so strong that light can no longer climb back out. This boundary is called the event horizon, and it acts like a one-way door. Things can go in, but nothing can come back out to tell the tale. Think of it as the edge of a waterfall. From upstream you can still swim, but once you pass the lip you are carried over and there's no returning the same way. The rule is simple: cross that invisible line and escape is impossible by any normal means. From the viewpoint of someone falling in, crossing the event horizon is unremarkable for a large black hole, no dramatic wall or flash, just a smooth continuation of motion. For an outside observer, however, the story looks very different. Light and signals from the falling object get stretched to longer and weaker waves as they climb out of the strong gravity. To distant eyes the infalling object appears to slow, redden and fade, seeming to freeze near the horizon. This odd mismatch happens because gravity changes how time and light behave. One person's quick drop can look like a permanent hover to another million miles away. The event horizon is not a physical surface you can touch, like a ship's hull or a planet's crust. It's a geometric boundary defined by the paths light can take. So there's no knock or barrier, you don't hit anything when you pass through. That said, gravity itself can do very physical things nearby. Close to a small, dense black hole the difference in pull between your feet and your head would stretch you lengthwise and squeeze you sideways, an effect often called spaghettification in plain talk. Near a supermassive black hole, by contrast, the same boundary can be farther from the center so the pull across your body might be gentle enough that you wouldn't notice much at the moment of crossing. Size matters a lot. The radius of the horizon grows with how massive the black hole is, so bigger black holes have larger, more gradual edges. A supermassive black hole's event horizon can be enormous, and you could cross it without immediately being torn apart. A smaller black hole, on the other hand, has a tiny but very steep edge where tidal forces become extreme almost immediately. Rotation also changes the neighborhood. A spinning black hole wins nearby space around with it, creating regions outside the horizon where things are forced to move with the spin. In everyday terms, that's like a whirlpool in water where you can get dragged along before you ever reach the central drop. Practically speaking, the event horizon determines what information can reach the outside universe. Anything past it cannot send a signal back, so it's a true point of no return for classical information. That doesn't stop scientists from studying the border itself. The way light bends and the dark silhouette a horizon casts make it possible for powerful telescopes to infer the presence and size of the boundary. Meanwhile, time dilation effects tied to strong gravity are not just theoretical. Similar principles are accounted for in technologies like satellite navigation, where clocks must be corrected for gravity's effects to keep positions accurate. The combination of invisible boundary, one-way behavior, and dramatic physical consequences near it makes the event horizon both simple in concept and rich in consequences. It's a clean dividing line in space that separates regions by what can ever be communicated back, and it gives rise to some of the strangest observational quirks in astronomy. In short, It's an invisible cliff with a strict, no-refund policy, and both gentle and savage experiences await depending on how big the cliff actually is. Singularity, theoretical core and its mysteries. Deep inside a black hole, the math of general relativity points to a spot where density and curvature shoot off to extremes and the rules we use to predict things simply stop working. This spot is what physicists call the singularity, a name that signals an edge of known physics rather than a comfortable, physical object you could point at. In plain language, it is where matter, as our equations describe it, would be crushed into such a small region that our current concepts of space and time no longer make sense. That does not mean there is literally an infinitely small point like a pin in space that you can poke, it means the theory gives nonsensical answers if you push it that far. We cannot look at a singularity directly because nothing, not even light, can climb back out across the event horizon, the black hole's point of no return. So all conclusions about the inner core come from theory and indirect clues, like how the black hole bends nearby light, how gas swirls around it, or the ripples in spacetime sent out when two black holes collide. These observations tell us about the neighborhood outside the horizon but stop short of giving a clear picture of whatever lies deeper. Think of it like getting alarmed by sounds from a sealed room. You can tell someone's moving around in there, but you can't see what they're doing. Because the singularity is where our equations fail, physicists expect that a better theory, one that combines gravity and quantum effects, would replace the troublesome, infinite answer with something finite and understandable. Several ideas attempt that, each with its own image. One suggests the core is more like a fuzzed-out region with no sharp point, another says matter could be transformed into an exotic state that takes up a tiny but non-zero amount of space. Some models even hint the collapse might bounce back in some form. These are not confirmed facts, though. They are carefully constructed possibilities that avoid the word infinite, and try to keep physical quantities finite so our predictions remain sensible. A practical way to think about the mystery: everyday materials behave predictably under pressure up to a point. Your car tire flexes, a soda can crumples, and a mattress compresses. But the conditions near a singularity would be orders of magnitude beyond any compression we can make on Earth, so known material behavior no longer applies. That's why lab analogies only go so far. We can mimic some aspects of curved spacetime with clever experiments, but we cannot reproduce the core conditions. It's like studying the rules of baking by watching a volcano. We can learn principles, but we cannot make the exact thing at home. There are also mathematical surprises depending on whether the black hole spins. In simple, non-spinning cases, the troublesome region is shrunk to what the equations call a point at the center. In spinning models, the mathematics can allow a more complex structure, such as a ring-shaped region, which leads to strange theoretical passages in the equations. Those solutions are interesting on paper, but they tend to be unstable when realistic effects are added. So many researchers think the simple, hidden, messy core picture, wrapped up inside the event horizon, is more likely. Either way, the singularity remains a place where familiar cause and effect breaks down, which is why physicists whisper terms like quantum gravity with a mix of hope and exasperation. Another important idea is the notion that singularities are safely tucked away from the rest of the universe. This is not proven, but the prevailing view keeps them hidden behind horizons so the outside world remains predictable. If that were not true, if a naked singularity could influence the outside, then the predictability of physics as we know it would collapse in practical terms. In short, keeping singularities hidden is good for making reliable predictions, much like keeping your secret cookie jar behind a locked cabinet is good for making sure your cookies stay put. We gain indirect knowledge about the interior by pushing other parts of physics to the limit. Observations of how matter behaves near the edge, and the waves produced when black holes collide, put constraints on how extreme the interior can be. Progress is steady rather than sudden, and theoretical work keeps narrowing the plausible scenarios. For now, the singularity is less a thing you can describe and more a signpost saying, "New physics needed here." It's a cosmic puzzle piece that refuses to fit into our current box, and that stubbornness is oddly motivating. After all, scientists love a good mystery, especially one that promises a new rulebook once solved. Types of black holes: stellar, supermassive, and intermediate. Astronomers group black holes by how big they are and how they probably formed, and that gives us three handy buckets to compare: the small ones born from stars, the enormous ones anchoring galaxies, and the middle-sized ones that are still a bit mysterious. These groups differ mainly in mass, where they hang out, and how we spot them with telescopes. Think of it as classifying animals by size: mice, elephants, and the animals in between, except the elephants live at the centers of galaxies and do not eat peanuts. Stellar black holes come from the collapse of very heavy stars when they run out of fuel and their cores fall in on themselves. They typically weigh a few to a few dozen times as much as our Sun, which makes them small by cosmic standards but still impossibly dense. Observationally, we see them when gas from a companion star falls in and heats up, glowing in 10th rays, or when two of them smash together and send out ripples in space that detectors can pick up. Picture a sink drain where water swirls into a tight whirlpool. A stellar black hole is like that whirlpool, compact and fierce, but it won't reach out and pull in the rest of your kitchen unless it happens to be right there. Supermassive black holes sit in the centers of most galaxies and are enormous, with masses that are millions to billions of times the Sun's. They are found by watching stars and gas orbit around an invisible, superdense point, or by spotting an extremely bright core when lots of material is falling in and heating up. These giants control the traffic in their neighborhoods and can shape whole galaxies, but they do not go roaming across space eating planets for fun. Imagine a city's central roundabout that everything moves around. The supermassive black hole is the roundabout, and the stars are the cars. They can be loud when feeding, producing bright jets and light, but otherwise they're mostly just sitting there holding the city together. Intermediate black holes fill the gap between stellar and supermassive, and that gap is where astronomers get curious. They would weigh something like hundreds to thousands of suns, and are suspected to lurk in dense star clusters or show up as unusually bright 10th ray sources. Evidence for them is weaker and more scattered. A few good candidates have been found, but confirming one is tough because their signals are fainter and rarer. Think of them as the awkward middle child of black holes, not tiny and nimble, not massive and obvious, just quietly hard to notice. Scientists are hunting for more with telescopes that can see 10th rays and with instruments that detect gravitational waves, because finding more of these middling objects helps explain how the very largest black holes might have grown in the first place. Formation: from star collapse to galactic giants. Massive stars stop making the pressure that holds them up once they burn the fuel that powers their cores, and that sets the stage for a dramatic collapse. As the core runs out of lighter elements it can fuse, it can no longer produce the outward push that balances gravity, so the center falls inward very quickly. The fall is sudden enough that outer layers can slam back outward in a bright explosion called a supernova, though in some cases the collapse is so complete that little light escapes and the star simply disappears into a compact object. If the collapsing core is light enough, the squeeze is halted by the weird quantum push of densely packed neutrons and the result is a neutron star. If it's heavier, gravity wins and a black hole forms. That threshold sits at only a few times the mass of the Sun, so only relatively massive stars reach it. Think of it like a crowd packed into a doorway. A few people can be held back easily, but once too many press forward the barrier gives way. The compact remnant left behind hides its center behind an invisible boundary often called the point of no return, where even light can't escape. Sometimes the collapse is accompanied by the star shedding its outer layers, and sometimes the star collapses almost silently in what astronomers call a direct collapse. Both paths can make a black hole. Binary systems add another twist. A star can lose mass to a companion over time, changing the final outcome and sometimes leaving behind a black hole that siphons matter from its partner, lighting up in 10th rays. Observations of pairs where one member is a compact, invisible object feeding on gas give clear, practical proof that stellar collapse makes black holes. Supermassive black holes, the giants at galaxy centers, are built by growth rather than a single collapse of one star. They can start as small seeds, either remnants of early, massive stars or as dense gas regions that collapse directly, and then grow by swallowing gas, dust, stars, and by merging with other black holes during galaxy collisions. Feeding a black hole is messy and bright. Swirling gas forms a hot disk that shines like a cosmic frying pan and can outshine the whole galaxy for a while. When a black hole eats fast, the light and wind from that hot disk can push away some of the gas and slow further growth, so the process balances itself in interesting ways. There's also room for intermediate steps between the small stellar black holes and the supermassive beasts. In dense star clusters, repeated collisions and mergers of massive stars or smaller black holes can build intermediate mass black holes that weigh hundreds to thousands of suns. Evidence for these middleweights is still being gathered, but they may act as stepping stones in the path from stellar collapse to galactic giants. In everyday terms, it's a bit like a local shop growing into a regional chain, then merging into a national brand over time, only with far more gravity and considerably less sensible business attire. Black holes don't act like vacuum cleaners roaming space. If the Sun were replaced by a black hole of the same mass, Earth would keep orbiting as before, though the sky would be very dark. What really creates the giants is a combination of an initial collapse that makes a compact seed and a long history of feeding and mergers that lets that seed become millions or billions of times more massive than the Sun. Humor aside, the story is one of collapse, accumulation, and sometimes chaotic feasting, a cosmic tale that starts in the death of stars and, given enough time and material, grows into the engines at the hearts of galaxies. Black hole spin and charge, Kerr and Reisner-Nordstrom basics. Black holes are defined by only a handful of properties that matter: mass, how fast they spin, and whether they carry an electric charge. Spin is simply the black hole's rotation, a twist in space itself, while charge is an excess of electric charge like the static cling after you pull a sweater off. A spinning black hole drags the spacetime around it, much like a spoon stirring honey. This is called frame dragging, and it means that things nearby are forced to move in the direction of the spin. A charged black hole produces an electric field, so particles with the same sign of charge will be pushed away and opposite charges pulled in, similar to how a charged balloon will attract small bits of paper. Rotating black holes are described by what scientists call the Kerr solution, which captures how rotation changes the region near the black hole in some striking ways. One of the most important new regions is the ergosphere, a squashed, donut-shaped zone outside the point of no return where space is being dragged so strongly that nothing can sit still relative to distant observers. You can picture the ergosphere like the crowded lane on a merry-go-round where you can't stand still without being swept around. That region allows clever tricks. In theory, objects can give up a bit of the hole's rotational energy and escape with more energy than they came in with, which is a neat way nature can tap the spin of a black hole. Practical consequence: spin affects how close matter in a disk can orbit before falling in. Faster, aligned spin lets material orbit closer, and that changes the light we observe from accretion disks. Charged, non-rotating black holes are captured by the Reisner-Nordstrom picture, which adds the influence of electric force on top of gravity. In this scenario there can be more than one characteristic surface around the central singularity, an outer horizon and an inner horizon, because the electric repulsion changes how space and time behave near the center. Think of it like two layers of protection created by competing forces, gravity trying to pull everything in, and electric repulsion pushing like charges back out. In real astrophysical settings, though, black holes are not expected to hold large net electric charge for long. Plasma around them contains both positive and negative charges, and if the hole gets a bit charged it will attract opposite charges and neutralize fast, like a sticky flypaper that catches whatever will cancel its charge. So charged black holes are a useful theoretical tool, and they show how electromagnetism would combine with gravity, but they're not the typical case we expect to see out in space. When spin and charge are both present, the full picture is richer and more complex. The combined solution that describes a rotating, charged black hole has features from both types, altering horizons and the shape of nearby spacetime. Magnetic and electric fields around a rotating hole can interact with the inflowing gas in ways that help launch jets, narrow, fast streams of particles, from the region near the hole. It's a bit like twisting a garden hose while holding a magnet nearby. The twist and the field together can guide the stream. In practice, astronomers estimate black hole spin by studying the 10th ray light from the inner edges of accretion disks and by reading the details of gravitational waves from merging black holes. Those observational tools act like forensic instruments, letting researchers infer how much twist a hole has without ever touching it. Simple analogies help. A spinning black hole behaves like a powerful whirlpool in a river that pulls boats into the flow and forces them to turn, while a charged black hole behaves like a very strong electrostatic balloon that repels or attracts charged particles. Humor aside, the key practical takeaway is this: spin is common and observable. It changes where matter can orbit and can power energetic phenomena, whereas charge is typically neutralized and mostly enters theory as a way to test how gravity and electromagnetism interact. Both concepts expand our understanding of how extreme gravity works, and both lead to clear, testable differences in the light and radiation we detect from the neighborhoods of black holes. Accretion disks, cosmic whirlpools of gas and light. Around many black holes there is a flat, spinning band of gas and dust that shines because the material rubs together and heats up as it slides inward. This ring forms because the falling matter keeps some sideways motion, so instead of plunging straight in it circles the hole, like water circling a drain before slipping away. A bathtub whirlpool or a washing machine spin cycle gives a good everyday picture. Stuff goes round and round, collisions happen, and heat builds up. It's messy, bright, and a little dramatic, exactly the sort of scene you'd expect when gravity and gas get into an argument. The hottest parts sit closest to the hole and can glow in very energetic light. Farther out the disk is cooler and emits visible or infrared light. In systems where the black hole is about the size of a star and feeding fast, the inner disk can become so hot that it produces 10th rays. Big black holes sitting at the centers of galaxies tend to make disks that shine more in ultraviolet and visible light, and when those disks are especially bright we call the whole system an active galactic nucleus or quasar. Telescopes that see high-energy light and instruments that image radio waves both help scientists read the light coming from different parts of the disk, and the Event Horizon Telescope, for example, captured a bright ring of emission tracing hot gas near a giant black hole's shadow. Friction between neighboring streams of gas is only part of the story. Magnetic forces play a major role too, acting like invisible rubber bands that tug on charged particles and let angular momentum move outward so matter can spiral inward. Think of stirring honey versus water. The stickiness, or lack of it, changes how the fluid moves. In an accretion disk, that stickiness comes partly from tangled magnetic fields and partly from turbulence, tiny eddies that mix things up and let gas lose speed and fall closer to the hole. The shape of the disk matters as well. Some disks are thin and pancake-like, letting light escape more easily, while others puff up into a thicker, puffed donut shape that traps radiation and behaves differently. Light from the disk can flicker and vary, sometimes on very short timescales and sometimes more slowly, and those changes are useful. Rapid flickers point to small, close-in regions. Slow, steady changes suggest a much larger, more distant structure. Observers use these brightness changes, plus the color of the light and how matter orbits in the disk, to estimate properties like how massive the black hole is and even how fast it is spinning. Powerful, narrow jets of particles often shoot away perpendicular to the disk, like a high-pressure garden hose aimed out of the system, and those jets are tied to the disk's magnetic setup and to how much gas is flowing in. Scientists recreate some of the physics on computers and in lab experiments to test ideas, because watching a real accretion disk evolve can take all sorts of timescales and tends to be noisy. Practical knowledge from these studies helps explain not only distant quasars but also the 10th ray flicker from a nearby binary system where a black hole feeds on a companion star. And while the whole picture can sound like cosmic plumbing, it's really a powerful natural engine, gravity, motion, and magnetism working together to turn falling gas into light, sometimes politely glowing and sometimes dramatically flaring, with a touch of chaos and, if you like, a sense of cosmic style. Relativistic jets, high-speed beacons across space. Some black holes launch narrow beams of matter and light that travel at speeds very near the speed of light. These streams are not gentle breezes, they are focused, high-energy outflows that act like cosmic searchlights, visible across vast stretches of space. The name relativistic just means the speeds are so high that effects from Einstein's theory of relativity matter, but you can think of it simply as extremely fast. Telescopes pick them up in radio waves, visible light, and 10th rays, so astronomers use them like signposts to find active black holes. The jets are born from chaos falling into order. Gas and dust spiral into a flat, whirling disk around the hole and get heated and ionized, turning into charged particles. Magnetic fields around that spinning disk gather and line up the flow, squeezing it into thin streams that shoot away from the poles. In everyday terms, picture a garden hose with strong pressure and a nozzle that makes the spray straight and narrow. Swap water for tiny charged particles and add a magnetic nozzle, and you get the idea. Sometimes the black hole's spin helps, too, nudging energy into the outgoing flow like a merry-go-round, giving a shove to anyone trying to jump off. Observationally, these jets can be bright and stubbornly persistent. When a jet points toward Earth, it looks especially intense, because of a trick of physics that boosts its apparent brightness, making some black hole systems shine like bad headlights aimed straight at you. Astronomers give those particularly flashy cases a nickname, but the important point is that orientation matters. Instruments on the ground and in space map jets at different wavelengths. Radio dishes trace the large-scale structure, while 10th ray and optical cameras reveal the hottest, fastest parts closer to the source. A few well-known jets are so prominent that they show knots and wiggles, evidence of shocks and instabilities, like bumps and eddies in a fast river. Jets do more than look dramatic, they shape their surroundings. By pushing and heating gas in a galaxy, they can slow or even stop new stars from forming, acting like a giant leaf blower rearranging the yard. That feedback is crucial for how galaxies evolve, and it helps explain why some galaxies stop making stars while others keep going. Jets also carry energy and magnetic fields far out into intergalactic space, stirring the gas between galaxies and seeding it with cosmic rays. In short, they are both cosmic beacons and agents of change, useful for pointing out a black hole and for changing the neighborhood it lives in. A little cosmic irony: something that forms from collapsing material can end up blowing matter and energy back out, like a dramatic sneeze after a very bad meal. Gravitational lensing, seeing through curved space. Mass bends the paths of light, so a very heavy object between us and a distant light source can act like a giant magnifying glass in the sky. Think of light as travelers trying to walk in a straight line, but the ground itself is a little curved, so their paths bend. A simple kitchen example helps. A spoon will make your face look stretched and multiplied when you hold it up. Gravity does the same trick to starlight, only the spoon is a galaxy or a cluster of galaxies and the stretching comes from gravity instead of metal. There are a few ways this bending shows up, with each one useful in a different way. When alignment is just right, a single distant galaxy or star can appear as several copies or as a stretched arc, even forming a near-perfect ring. That ring is basically a natural zoom lens, and it can make extremely faint objects bright enough to study. More subtle bending slightly distorts the shapes of many background galaxies, and by measuring those tiny distortions across large patches of sky, astronomers can trace where the invisible mass sits. A quick and funny analogy: weak lensing is like seeing a field of coins under slightly warped plastic wrap. Each coin looks a bit off, and the pattern of distortion tells you where the bumps are. A third flavor is microlensing, which happens when a relatively small object, like a lone star or planet, drifts in front of a background star and briefly brightens it. It's like a tiny magnifying glass passing over a distant lamp. The light gets stronger for a short while and then returns to normal. Astronomers use that brightening to detect planets that would be nearly impossible to see any other way, including planets that don't shine on their own. This method is especially handy for finding planets that are far from their stars or free-floating, because the effect depends only on gravity, not on light from the planet itself. Practical uses of this cosmic lensing are surprisingly concrete. Mapping the subtle distortions across millions of galaxies reveals the overall distribution of mass, including the invisible stuff we call dark matter. That mapping is a direct way to see where gravitational pull is strongest even when there's nothing glowing there. Lenses also let us peer into the very distant universe by magnifying feeble galaxies and quasars, giving a clearer look at objects that would otherwise be beyond our telescopes. And when multiple images of the same source arrive at different times because the light took different routes, those time delays act like clues for how space is stretched on huge scales, which helps measure how the universe behaves. Spotting and using these effects takes detective work and sharp tools. Large sky surveys scan vast areas to find the characteristic arcs, rings, and sudden brightenings, while follow-up observations with high-resolution telescopes pin down the details. Computer models then untangle the lensing patterns to reveal the mass distribution that caused them. It's part astrophysics and part cosmic forensic science. The payoff is real. Gravitational lensing gives astronomers a natural telescope and a ruler for gravity, letting us study otherwise hidden structures and tiny objects far across space. And on the bright side, the universe provides the quirks, like twisted, duplicated galaxies, that keep scientists entertained, and occasionally laughing at the cosmos's sense of cosmic humor. Time dilation near black holes. Time slows down. Gravity bends time itself. Clocks run slower where gravity is stronger. Close to a black hole, where gravity becomes extreme, that slowing becomes dramatic compared with clocks far away. Physicists call this gravitational time dilation, and it is a real, measured effect, not science fiction jargon, so your watch would genuinely lag behind a friend's if one of you ventured near a massive object while the other stayed put. Near the edge of a black hole, the effects get stranger to an outside observer. Light climbing out loses energy and shifts toward longer wavelengths, so any signals from someone falling in become redder and dimmer. From far away, the falling person appears to slow down as they approach the invisible boundary, fading into a red blur and never seen to quite disappear. Short sentence. For the person falling, however, their own clock ticks normally and they cross that boundary in a finite amount of time without seeing the universe outside freeze. Everyday technology already accounts for this weirdness. Satellites that power navigation systems circle Earth at high speed and at different heights, and their clocks tick at rates that would cause serious errors unless corrections for both motion and gravity are applied. It's an ordinary, practical use of the same principles that make time behave oddly near a black hole. So while you can't use one to skip a boring meeting, engineers do rely on the same physics so your phone actually finds the right coffee shop. Tidal forces can add an uncomfortable twist. If the black hole is small, the difference in gravity between your head and toes can stretch you out. The colorful term is spaghettification, which is unpleasant and very final. For very large black holes, that stretching near the edge can be negligible, meaning you might cross the boundary without feeling much at all. Reality check: crossing a black hole horizon doesn't trigger a visible whoosh or alarm in your pocket. Local physics still behaves locally, even when global time gets weird. This behavior of clocks and light is not just a thought experiment. Astronomers infer these effects by observing how light from the vicinity of massive objects is shifted and dimmed, and by modeling how matter moves and emits radiation under extreme gravity. You can think of it as time being elastic. It stretches and slows under weight, and in the case of a black hole that stretch becomes stretched out. A little funny, yes, but also profoundly useful to understand the universe and to keep our satellites on track. Tidal forces and spaghettification. Gravity doesn't pull the same on every part of an object when that object is close to a very compact mass. The side nearer the mass feels a stronger tug than the far side, and that difference is what causes tides on Earth and extreme stretching near black holes. On Earth, the moon and the sun create measurable ocean tides, which are just gentle examples of the same unequal pull. Think of the ocean rising and falling twice a day. That is a mild, friendly version of what happens in the neighborhood of a black hole, only cranked up until atoms themselves start to complain. Closer to a black hole, the unequal pull becomes so strong that an extended object is stretched lengthwise and squeezed sideways. Put two hands on a soft piece of taffy and pull them apart slowly. The candy thins and elongates as it stretches. The same basic effect applies to matter near a black hole, and people call that extreme stretching spaghettification, because the end result is long, thin strands of material. It's not a culinary trend, it's physics: long, thin, and not edible. Smaller black holes make the stretching happen very abruptly and violently, often before anything crosses the point of no return, while very massive ones spread their pull over a much larger region, so you might cross that boundary with little immediate sensation. In plain terms, a stellar-sized black hole will rip things apart well outside its invisible edge, whereas a monster black hole in a galaxy center can let objects pass the edge before intense stretching shows up. Astronomers actually watch stars get pulled into thin streams of gas in such events. Those shredded stars light up the sky as gas heats and glows when it falls inward, like nature's own blender left on high. When material is stretched, it doesn't simply vanish, it forms long streams that heat up through friction and collisions, and that hot gas radiates light, often in energetic tenth rays that telescopes on Earth and in space can detect. The stretched matter also spirals inward and can feed a bright disk or even launch energetic jets. For anything trying to stay intact, the outcome is grim. Internal forces are overwhelmed, structural bonds break, and communication back to the outside world ends once the point of no return is crossed. On a human scale, survival isn't realistic. Even before bones would bend, the tidal difference from head to toe would make ordinary movement impossible. You would be pulled into an orientation and stretched like taffy. That said, if a person could somehow approach a supermassive black hole very slowly and carefully, the initial sensation might be small, so small that a short-lived sense of calm could deceive you. Still, calm or not, the physics is unforgiving. The farther in you go, the stronger the differential pull becomes, and there is no safe way to resist it. Hawking radiation, black holes evaporating. Black holes are predicted to emit a faint thermal glow when quantum effects near their edges are taken into account. In simple terms, empty space is not totally empty. Tiny particle pairs pop into and out of existence all the time, a bit like brief bubbles on a calm lake. Near the boundary of a black hole, called the event horizon, one member of a pair can fall in while the other escapes, and that escape is what we call the radiation. This process removes a little bit of the black hole's energy, and since energy and mass are linked, the black hole slowly loses mass. In other words, it evaporates. The escaping particles behave like heat given off by an object. Larger black holes are colder and emit far less of this radiation than smaller ones. Small black holes are comparatively hotter and radiate more strongly. Think of it like two objects cooling. A giant iceberg takes a long time to warm up, while a hot pebble cools quickly. The same basic idea explains why a very massive black hole shines with an almost unimaginably faint thermal glow that we can't detect with current instruments. Laboratory analogs, experiments with flowing water, optical fibers, and ultra-cold atoms, have produced Hawking-like emissions in controlled setups, giving experimental support to the core idea without needing a real black hole. The word virtual, often used for those fleeting particle pairs, can be misleading, so let's keep it plain. Quantum fluctuations are temporary blips that usually cancel out, but the presence of a horizon can let one blip become real and escape. Energy conservation is respected because the partner that falls in effectively carries negative energy relative to the whole, reducing its mass. A household analogy is useful. If you remove tiny crumbs from a loaf one at a time, the loaf gets smaller. Here the crumbs are packets of energy carried away as radiation. A little humor helps. Think of the black hole sneezing out a photon now and then, and very, very slowly getting lighter. Not all consequences are tidy. If a black hole can vanish by losing mass this way, what happens to the detailed information about everything that fell in? That question sparked a long and lively debate among physicists, because ordinary quantum rules say information shouldn't just disappear. Many researchers today believe the information is preserved in some subtle way, though the exact mechanism is still a subject of active work and spirited argument. The conversation ranges from ideas that information comes out with the radiation to more exotic proposals where the black hole's surface or quantum gravity effects keep a record. Observationally, Hawking radiation has not been seen from real astrophysical black holes because the predicted temperature is extremely low for any black hole formed by collapsing stars. Searches for the explosive final bursts from tiny primordial black holes have been conducted, but no confirmed detections have shown up. That makes tabletop analog experiments and theoretical advances important for testing and refining the idea. In short, the basic mechanism is well motivated and mathematically robust, the consequences are profound and sometimes puzzling, and the hunt for direct evidence continues, with physicists as eager as detectives, minus the trench coats. Black hole thermodynamics and entropy. Black holes act like ordinary thermal systems in an odd way. Quantum effects give them a temperature and an entropy, so they're not just cosmic vacuum cleaners. This temperature comes from tiny quantum processes near the event horizon that allow particles to escape, making the hole slowly lose energy over very long times. The entropy associated with a black hole is not measured by how much stuff is inside, but instead by the area of its outer surface, the event horizon. That's a key fact and it upends our everyday intuition, because regular objects store more disorder with more volume, while black holes store it on a surface. Think of entropy as a count of how many different microscopic ways the same macroscopic object could be arranged. For a shuffled deck of cards there are countless orders, for a bedroom, there are many messy arrangements, for a black hole, the number of possible internal arrangements, what physicists call microstates, turns out to be enormous and, surprisingly, tied to the surface area. In plain terms, double the horizon area and you double the entropy. It's like a hard drive where the storage capacity is set by the size of the casing, not how deep the drives go. This is the root of the holographic idea. The information describing the inside can be encoded on the surface, similar to how a hologram stores a 3D image on a 2D plate. Laws of thermodynamics have neat counterparts for black holes, and these analogies help make sense of exotic behavior. For example, the concept of temperature corresponds to a property called surface gravity, which measures how strongly the black hole pulls at its horizon. Higher surface gravity means higher temperature. Energy changes in the hole, adding mass or angular momentum, relate to changes in that surface area, so the usual bookkeeping of heat and work has a sibling in black hole physics. Classically, the horizon area can only stay the same or grow, much like entropy in isolated systems tends to increase. Quantum effects give a twist by allowing a slow decrease through radiation, so the full picture blends classical and quantum rules. The idea that information might be lost when something falls into a black hole creates a real puzzle. If the hole evaporates away via its tiny temperature-driven radiation, where does the information go? Some ideas suggest the information is encoded on the horizon and slowly released, others point to deep quantum entanglement between inside and outside, and still others propose that a complete description of the system lives on a boundary in a lower number of dimensions. These are technical paths, but they share a common practical feel. We're trying to reconcile how information, which we treat like a conserved bookkeeping of possibilities, is preserved in a universe where gravity and quantum rules meet. Picture dropping a book into a shredder. The paper is gone but the pattern of ink is still, in principle, recoverable if you had the right kind of microscopic record. That's the kind of recovery scientists are chasing, with a dash of theoretical humor about whether nature keeps receipts. Everyday analogies help but don't replace math. Still, they highlight striking consequences. Since smaller black holes are effectively hotter, they radiate faster. A tiny, hypothetical hole would be far more energetic than a supermassive one, though astrophysical holes are so massive their temperatures are practically zero to us. Attempts to count the microscopic states that give rise to a black hole's huge entropy have had success in specific theoretical models, showing that the area rule can emerge from underlying quantum structures. So the picture that emerges is practical and strange at once. Entropy, information, temperature, and geometry are all linked at the horizon, and understanding that link better could change how we think about information, space, and even the rules of physics themselves. The information paradox, puzzle at the edge of physics. Black holes are predicted to give off a very faint glow of particles even though nothing can escape from inside their deep grip, and that surprising fact creates a real puzzle about whether the detailed description of anything that falls in, what physicists call information, can ever be lost. In simple terms, information means the complete recipe for a system, what particles were where, how they were spinning, and so on. Quantum theory says recipes are never truly destroyed, they can be scrambled, but in principle you could reconstruct the original. Gravity, as described by Einstein, makes a black hole look like a one-way trap that swallows everything and then, as it slowly fades, leaves behind only a bland, steady glow. That clash is the heart of the paradox. To make the tension more down-to-earth, think of a paper letter shoved into a shredder versus burned to ash. When something is shredded, you can, with time and patience, tape the pieces back together and read the letter again. When something is burned it seems gone. But in physics, even burned paper leaves telltale traces in the smoke and heat. With enough cleverness you could, at least in theory, work backward. The trouble with black holes is that the radiation they emit looks like plain thermal noise, like white static on an old radio, which gives no obvious clue about the original letter. If that noise is truly random, then the detailed story of what went in would be lost forever, and that breaks the rules of quantum mechanics. Several ideas try to reconcile the rules. One suggestion is that the outgoing radiation is not purely random but carries subtle correlations that encode the information, much like tiny fingerprints hidden in static. Another idea says the information lives on the black hole's boundary, not inside, similar to how a movie on a flat screen can represent a whole three-dimensional scene. The screen holds all the information even though you perceive depth. A third possibility is that tiny remnants remain after a black hole evaporates and keep the information safe. Each of these pictures has pros and cons, like competing solutions to a riddle where every answer seems to annoy someone at the physics party. Entanglement, the quirky quantum connection that links particles across space, plays a starring role in modern thinking about the problem. In normal life, entanglement is nothing like magic. It's more like two perfectly synchronized clocks that stay matched even when you can't see how they communicate. If the particles in the radiation are entangled with those that fell in, then tracking those quantum links might allow the information to be reconstructed from the glow. Recent theoretical work argues that when you account carefully for those links and how space and time get reshaped by quantum effects, the radiation can gradually reveal the story. That is promising. It's like realizing that the static on the radio actually has a pattern if you slow it down and listen the right way. None of this changes your morning commute. You won't lose your keys to a black hole, and your phone won't dissolve into quantum foam. Still, resolving the paradox is not a minor bookkeeping issue. It tests whether our best descriptions of the very small and the very large can be made to agree. Solving it could point the way to a deeper theory that blends gravity and quantum rules, a Frankenstein marriage the universe keeps insisting should work smoothly. Physicists continue to debate and refine ideas, and while the answer isn't settled, progress looks like peeling back more layers of a mystery cake. The flavor is odd, but the cake is tantalizing. Firewalls, complementarity, and competing solutions. When people talk about how black holes treat quantum information, they are really pointing to a clash between two well-tested ideas: quantum mechanics, which says information is never destroyed, and the smooth spacetime picture of gravity, which says you can cross a black hole's edge without fanfare. This tension is not just academic, it forces theorists to propose radically different pictures of what actually happens at the black hole's boundary. Think of it as a disagreement about whether a door hides a calm room or a surprise bonfire on the other side. Simple analogy: if you burn a book on one side and sweep the ashes to the other, is the story gone or somehow encoded in the ashes? That question lies at the heart of the proposals below. One proposed resolution says there is a searing wall of high-energy particles right at the horizon. In plain terms, instead of falling through smoothly, an astronaut would be incinerated by an invisible firewall. This idea solves the bookkeeping problem of quantum information because the violent region would scramble and release information back out with the outgoing radiation, so nothing truly gets lost. The trade-off is dramatic. It violates the usual expectation from gravity that a freely falling observer feels nothing special when crossing the horizon. Imagine opening your front door and finding a blast furnace instead of a hallway. It fixes one problem but ruins the pleasant surprise of walking through a door. Critics point out that creating such a wall seems to contradict a cornerstone of gravity's description of smooth space, so the firewall remains controversial and uncomfortable for many physicists. A very different approach keeps the horizon smooth for the person falling in, while saying that observers outside see information encoded on the black hole's surface in a way that makes no contradictions appear. This idea, called complementarity, treats the two descriptions as complementary but never simultaneously accessible. The outside observer watches information smear thinly over the surface, like a message smeared across a windowpane, while the infalling observer experiences ordinary physics and doesn't notice anything odd at the border. A helpful everyday example is two people watching the same play from different seats. One sees the actors' faces up close, the other sees choreography and lighting. Neither description needs to be combined to get contradictions. Complementarity avoids a burning astronaut, but it stretches our sense of how objective reality should be, and critics argue that certain quantum correlations would still force an inconsistency unless additional mechanisms are added. String-inspired alternatives replace the neat horizon with a Messier microstructure. Instead of a smooth ball with an empty interior, the black hole becomes a fuzzball made up of many configurations that extend to where the horizon would have been. In this picture there is no sharp edge to cross, information is stored across the fuzz. Picture a knitted sweater rather than a perfectly smooth leather ball, the stitches themselves carry the pattern. That makes it easier to see how information might escape without invoking fire or observer-dependent descriptions. The fuzzball idea gives a concrete model in some theoretical frameworks, but it depends on the details of those frameworks and on whether the same picture can apply to all black holes in our universe. It's elegant, but not universally accepted. Other proposals take subtler routes. One idea is that a black hole's surface can carry low-energy imprints, sometimes called soft hair, that encode information in tiny wiggles of the surrounding fields. Think of these as fingerprints on a glass door. They're small, but they could carry plenty of identifying detail if you look carefully. Another speculative route connects quantum entanglement and geometric shortcuts. Entangled particles might be linked by tiny wormhole-like connections so that information is never truly lost but subtly shared between inside and outside. These suggestions are less flashy than a firewall and less radical than giving up a horizon entirely, but they require new ways to track delicate quantum correlations in a violent gravitational setting. Which picture will win is still unknown, and each option has practical consequences for how theorists calculate and what kind of signals we might look for in gravitational waves or in hypothetical signatures of Hawking-like radiation. Observational tests are hard because the effects are subtle and the direct processes are extreme and distant. Still, the competing solutions have driven advances in our understanding of quantum information, chaos, and how gravity might weave together with quantum theory. The debate has a playful side too. Physicists frequently swap metaphors: burning doormats, knitted sweaters, fingerprinted glass, because when the math is heavy, humor helps keep the mind limber. Quantum gravity candidates, string theory and loop quantum gravity. Both approaches try to explain the same hard fact: the rules of the very small, quantum mechanics, and the rules of the very large, gravity, clash near black holes, and something new is needed to describe that clash. String theory pictures the basic bits of the universe as tiny, vibrating strings instead of point particles. Strings vibrate in different ways and those vibrations show up as the particles and forces we see, much like different guitar strings or different fingering produce different notes. For black holes, collections of strings and higher dimensional sheets, called brains, can combine into many internal configurations, and counting those configurations can reproduce the amount of disorder, the entropy, that a black hole appears to have. A neat trick from string theory is a kind of holographic idea. A complicated gravitational problem inside a volume can be mapped to a simpler quantum system on the boundary, similar to describing a 3D object by its 2D shadow. This gives a concrete way to track where information might go when matter falls into a black hole. Loop quantum gravity takes a very different starting point. It starts by slicing space itself into tiny chunks, not by adding new kinds of particles. Picture space woven from threads or built out of Lego blocks. Those threads connect at nodes and form a network. Each link and node carries a small, discrete amount of area or volume, so surface area and volume are not smooth continua but come in little steps. When you apply that idea to a black hole horizon, the horizon's area becomes a sum of these tiny pieces, which helps explain why entropy scales with area, like counting tiles on a floor to measure how big the floor is. Loop quantum gravity also suggests that the infinitely dense singularity inside a black hole is replaced by a region where quantum geometry takes over and the classical picture breaks down, so the worst infinities go away. Both frameworks offer ways to address the information question that bothered physicists for decades. String theory often argues that the microstates of strings and brains store the information, and the holographic mapping shows how information can be preserved even as the black hole radiates. Loop quantum gravity suggests that because space and time are discrete, the deep interior may evolve in a way that avoids destroying information outright. Neither claim is a finished story. Think of them as promising blueprints rather than certified building plans. Experimental proof is the bottleneck. Directly probing the tiny scales where quantum gravity matters is far beyond current particle accelerators, so researchers look for indirect signs, tiny imprints in black hole radiation, subtle deviations in gravitational waves, or signatures in the patterns of the early universe. So far, no definite smoking gun has shown up. A few practical contrasts help keep the picture clear. String theory aims to be a full unifying framework that naturally includes particle types and forces, so it builds on extra dimensions and a larger mathematical toolbox. This makes it flexible but also complex. Loop quantum gravity focuses very tightly on quantizing spacetime itself without assuming extra dimensions or embedding structures. That gives it conceptual clarity but leaves open how to include all particle types naturally. An everyday analogy, string theory is like trying to write a single recipe that covers every dish, while loop quantum gravity is like perfecting the texture of the bread before worrying about the fillings. Either way, both ideas try to turn abstract math into testable physics, and both continue to inspire creative experiments and new ways to think about what a black hole really is. In short, string theory and loop quantum gravity offer different lenses through which black holes might be understood, vibrating strings and holographic maps on one side, a patchwork of tiny chunks of space on the other. They are tools, not final answers, and each has strengths, weaknesses, and a few charming metaphors that make the universe feel slightly less intimidating. Numerical relativity and simulating mergers. Simulating two black holes spiraling into each other means letting a computer solve Einstein's equations step by step across space and time, because those equations are too complicated to do on paper when things get violent and fast. These are partial differential equations that tell you how space and time bend and move, and the computer divides space into a grid or uses smooth mathematical pieces and then marches forward a little bit of time at a time to see what happens. Think of it like predicting weather, but instead of clouds and wind you predict how spacetime stretches and sends out ripples. The output is a detailed waveform that shows how the gravitational waves rise and fall as the objects orbit, crash together, and settle down. Setting up a realistic run starts with clean initial data, two black holes with given masses and spins placed in a slice of space that already satisfies certain constraint equations, so you don't accidentally start with impossible geometry. One common trick treats the singular centers as punctures, and evolves the surrounding space while ignoring the infinities inside, kind of like sketching the edge of a sinkhole without falling in. Another approach carves out the interior region entirely, which removes the troublesome core from the computation but requires careful boundary conditions at the cutout surface. Both methods are tools to avoid the literal infinities that black holes bring to the party. The way the equations are written and the coordinates you pick matter a lot, because bad choices can make the computer crash even when the physics is fine. Researchers recast Einstein's messy equations into forms that behave well for numerical stepping. Some forms spread errors safely, others keep constraints under control. That's similar to choosing whether to drive by following a simple GPS route or by reading a complicated map while juggling coffee. One approach makes life easier for the machine. Gauge conditions, which are just choices of how to label point-by-point positions in spacetime, are like picking a good camera angle. The picture gets clearer and the simulation runs more smoothly. Computers use different numerical techniques depending on the goal. Finite difference methods compute derivatives by comparing nearby grid points, which is intuitive and robust. Spectral methods represent the solution as smooth waves built from basis functions and can be extremely precise when things are smooth. Picture replacing a pixelated photo with a glossy poster made from some sine and cosine waves. Adaptive mesh refinement, a practical necessity, concentrates computing power where it's needed most, close to the holes and along the outgoing gravitational wave front, while using coarser resolution in quiet regions, much like focusing a camera lens on the main subject and letting the background blur. Hybrid strategies combine full numerical runs with faster analytic approximations to cover all stages of the merger. Early on, when the objects are far apart and moving relatively slowly, simple equations give good results. The final moments, when gravity is brutally nonlinear, demand full numerical power. Scientists stitch these pieces together to make waveform catalogs used by detectors. Those catalogs act like a music library for gravitational wave observatories. The detector listens to the universe and matches incoming signals to the closest waveform to identify the source and measure its properties, such as the two bodies' masses and spins and the final remnant spin. Including matter makes things even more complex. When at least one partner is a neutron star, the simulation must track fluid motion, heat, magnetic fields, and radiation like neutrinos. That requires coupling Einstein's gravity solver with specialized codes for hydrodynamics and microphysics, an expensive multi-tool setup that pushes supercomputers hard. Results from these runs predict not only gravitational waves but also electromagnetic fireworks, like short bursts of gamma rays or kilonova light, which help astronomers connect different kinds of observations. Validation and cross-checks keep the field honest. Independent groups run the same scenarios with different codes and methods to make sure results agree within expected uncertainties. Simple tests, convergence checks, and comparisons to known limits build confidence that the simulated waveforms are trustworthy when used for real data analysis. It's the computational equivalent of taste testing a recipe by several cooks before putting it on the menu. Running these simulations is resource-intensive and requires careful planning, but the payoff is big. Accurate waveforms let detectors extract precise information from faint signals. They also help answer practical science questions, like how much energy is carried away by the waves and what the final black hole looks like. And while the machines doing the heavy lifting aren't glamorous, the results let us watch a cosmic collision with more clarity than any telescope could provide, sort of like using a slow-motion camera to see the last dramatic twirl in a dance. Gravitational waves, ripples from black hole collisions. When two black holes chase each other and finally collide, they shake the very fabric that holds space and time together and send out waves that travel across the universe. These waves are called gravitational waves, which you can think of as wrinkles moving through spacetime rather than ripples in water. They move at the same speed light does, so the signal reaches us as fast as anything possibly could across cosmic distances. In many cases the collision itself doesn't throw off light or heat, so these ripples are often the only way to know the event happened. Detectors on Earth pick up those tiny wiggles using lasers and mirrors. A basic idea: a single laser beam is split and sent down two long tunnels at right angles, bounces off mirrors, and then comes back together. If one tunnel gets microscopically shorter while the other gets microscopically longer, the pattern of the light changes. That change is what scientists look for. It's a bit like noticing that two identical watch hands are slightly out of sync because a friend bumped the table, only you're measuring lengths far smaller than anything you can see without special instruments. From the shape of the wave we learn concrete things about the colliding pair. The rise and fall of the signal tells us how massive the black holes were, whether they were spinning, and how fast they were moving as they met. When the signal is converted into sound, it often makes a distinctive chirp that rises in pitch, short and sharp for smaller black holes, deeper and longer for bulkier ones. Scientists match the incoming pattern to a library of predicted wave shapes, similar to matching a hum tune to a song in a playlist, and that matching gives details about the merger. Collisions of black holes don't usually light up the sky, so gravitational waves are a unique messenger. Networks of detectors spread around the globe act like ears at different locations and can tell roughly where a wave came from, much as several people clapping at once can help you guess which direction the noise came from. Plans to add more sensitive instruments on the ground and to put detectors in space will widen the range of black hole collisions we can hear. Ground-based observatories are tuned to smaller, faster crashes, while space-based ones will listen for the slow, deep thumps produced when supermassive black holes combine. In short, gravitational waves are a new kind of cosmic sound, and each detection is another clue about the most extreme objects out there. Observational evidence, from 10th rays to the Event Horizon Telescope. Astronomers find black holes by what they do to nearby stuff, not by looking at the hole itself. When gas orbits a black hole, it gets squeezed and heated until it shines in 10th rays, which are like superhot light beyond what our eyes can see. Space telescopes tuned to 10th rays, for example Chandra, XMM Newton and New Star, watch bright flashes and steady glows from these hot disks, telling us where matter is piling up and falling in. Think of it as the cosmic version of a frying pan. Crank up the heat and things start to glow. Some of the clearest 10th ray signatures come from binary systems where a normal star feeds gas to a compact companion. Cygnus 10th 1 is a famous example where the light from the gas shows it spiraling into something too small and heavy to be a normal star. The inflow forms a spinning, pancake-like disk and a separate hot corona above it that spits out high-energy 10th rays. It's a bit like a blender with a hot lid, messy, loud, and obvious if you're standing nearby with an 10th ray detector. Sudden bright flares, known as outbursts, occur when more material dumps in and the whole system lights up. Radio and optical observations show other pieces of the puzzle. Some black holes launch narrow, powerful jets that beam material and energy far beyond their host galaxy. These jets glow strongly in radio waves and can be mapped with arrays like the Very Large Array. One giant galaxy displays a jet so prominent it can be seen from many instruments across the spectrum. Combining radio, infrared, optical and 10th ray views is like walking around a sculpture and seeing every side. Each wavelength reveals a different layer of the black hole environment. Short and simple, different lights, different stories. The Event Horizon Telescope works differently. Many radio telescopes spread around Earth lock onto the same target and combine their signals to act like a single, Earth-sized dish. This technique, called very long baseline interferometry, lines up signals using precise timing and turns lots of small dishes into one enormous one, giving incredibly fine detail. The resulting images show a dark central region, a shadow, surrounded by a bright ring of glowing gas, which matches what physics predicts for light close to an extremely compact mass. The EHT also measures the orientation of the light, revealing magnetic fields near the hole. In human terms, it doesn't just take a selfie, it reads the mood rings. Other kinds of evidence add confidence. By tracking stars that whip around a tiny region in a galaxy center, astronomers infer a huge mass packed into a very small space. Those stellar orbits are like moths flying very fast around an invisible lamp. Gravity also bends light from background objects when a massive compact object sits in the foreground, producing stretched or multiple images, similar to looking at something through a thick glass paperweight. Put together, 10th rays that mark hot infalling gas, radio and optical maps of jets and surroundings, the high-resolution shadow from the Event Horizon Telescope, and star motions all form a consistent, practical picture. Black holes may be invisible, but they leave plenty of very loud footprints. The image of M87 and the shadow of SGR-A**. Astronomers produced a clear ring of light around a dark center when they observed M87, revealing the glow of hot gas circling a massive gravity well and the dark silhouette that marks where light can no longer escape. That dark shape is called a shadow not because something physically blocks light like a hand, but because the black hole's gravity bends and swallows nearby light, leaving a dim region surrounded by bright, glowing gas. The bright ring looks lopsided in places because some of the gas is moving toward us faster than other parts, making that side appear brighter, much like how a spinning carnival ride looks different depending on whether a car is coming toward you or moving away. The center of our own galaxy shows a similar dark silhouette, but it behaves very differently. Gas and dust near that black hole whip around on much shorter timescales, so the appearance changes quickly, flickering, shifting, and never staying perfectly still. Think of it as comparing a slow, majestic lava lamp to a quickly boiling pot, one gives you a steady pattern, the other is restless and always rearranging itself. Because of that restlessness, getting a clean picture requires special techniques that can freeze the motion and reconstruct the underlying shadow. Capturing these views relied on linking many radio telescopes across the globe so they work like one giant dish, a trick that lets observers see incredibly fine details despite the vast distances involved. Each dish records radio waves and precise timing. Later all those recordings are combined with powerful algorithms that fill in missing information, like completing a large jigsaw puzzle when many edge pieces are already gone. The result depends on both the hardware and clever software, and the image you see is the best interpretation of the sparse data, not a simple snap from a single camera. These images do more than look cool, they let scientists test how gravity behaves under extreme conditions and check whether our equations for light and motion are holding up. Models that predict the ring size and shape are compared to observations, and so far the match has been a strong thumbs up for our current understanding of gravity. For the rest of us, it's a reminder that black holes are not invisible monsters but dynamic systems, behaving like cosmic furnaces that throw off light and heat right up to the brink, somewhere between a dramatic sci-fi skyline and a very expensive espresso machine working overtime. Measuring mass and spin, how we weigh black holes. Mass and spin are what astronomers focus on when they want to describe a black hole, because these two traits largely determine how it behaves. Mass tells you how much stuff is packed into it, and spin tells you how fast that stuff is twirling. Scientists measure mass mostly by watching how something else moves under the black hole's pull, a very basic idea, like weighing a hidden object by watching how a friend walks around it while holding a rope. One common and clear method is to track the orbits of stars or gas that circle a black hole. If a star makes a tight loop, the speed and shape of that orbit reveal the mass inside, using the same simple physics that governs planets around the Sun. In practice, astronomers watch the star's motion and use the relationship between orbital speed and distance to get the weight of the invisible object. A neat, everyday analogy is measuring how fast a car must go to stay on a curved on-ramp. The sharper the turn for the same speed, the stronger the pull inward. When a black hole has a bright disk of hot gas around it, that disk becomes a useful tool for both mass and spin. The inner edge of the disk sits where bright light stops being produced, and that position shifts depending on how fast the black hole spins. Faster spin pulls the disk closer in, and the hottest gas then emits 10th rays with a particular shape. By fitting models to the 10th ray light, a method called continuum fitting, scientists infer how close the inner disk reaches and thus estimate spin. Another 10th ray trick looks at a special fingerprint in the spectrum, a narrow iron emission line that a spinning, relativistic disk stretches and skews. The way that line is smeared gives clues about both speed and gravitational effects near the hole. Think of it as checking the blur in a photo to tell whether the photographer moved their hand or the subject was spinning. Gravitational waves bring a very different kind of measurement to the table. When two black holes collide, the ripples they send through space carry a detailed record of their masses and spins. Detectors on Earth read those ripples like a barcode, the waveforms rise and fall, the chirping pitch, and the tiny wiggles encode how heavy and how fast each partner was spinning just before they merged. This is powerful because it doesn't rely on light at all, useful when gas is absent or faint. Still, every method has limits. Disk-based techniques depend on assumptions about the disk's thickness and magnetic fields, orbital methods need a visible tracer such as a star or gas cloud, and gravitational wave inferences get muddled if spins are tilted or if one object is much smaller than the other. To make these ideas more tangible, measuring mass by orbits is like timing a child on a swing to figure out how strong the playground pole is holding it. Measuring spin with 10th rays is like deducing how fast a washing machine drum is spinning from the pattern of water splashes on the window, and reading gravitational waves is like listening to the note a bell makes after being struck to tell what metal it's made of. Scientists combine these approaches when possible, cross-checking results and improving confidence. Humorous as it sounds, black holes don't hand over a receipt, so astronomers must be clever, patient, and a little bit like detectives piecing together invisible evidence. Black holes and galaxy evolution, cosmic feedback. At the hearts of many galaxies, a compact but powerful engine can push gas and heat out into the surroundings, and that push changes how new stars form. The engine is a black hole that is actively feeding. As gas spirals in it releases enormous energy, some of which escapes as fast winds or narrow jets that punch through the galaxy. These jets and winds act like cosmic gardeners, pruning and reshaping the supply of cold gas that would otherwise collapse into newborn stars. Sometimes they gently nudge the gas, other times they blow whole clouds away, leaving the galaxy quieter. This outflow can heat the gas that fills a galaxy and its halo so the gas cannot cool and condense into stars. Picture a pot of soup left to cool. If you keep stirring and adding heat, the steam never settles. Likewise, when energy from the black hole keeps the surrounding gas hot, the reservoir for star formation dries up. Observers see clear signs of this process. 10th-ray images reveal cavities or bubbles carved in hot gas by jets, while radio telescopes map the jets themselves and optical spectra show gas being pushed at high speeds. A famous nearby example displays a narrow bright jet visibly stretching out from the galaxy center, and that jet lines up with cavities in the surrounding hot gas, direct evidence of mechanical feedback at work. In other cases, the central engine's radiation acts like a powerful fan, sweeping out or ionizing the cold clouds where stars would be born. When the black hole lights up as a quasar, intense light and winds can drive gas out of the galaxy's inner regions. This radiative mode can be surprisingly efficient at clearing fuel for star formation, which helps explain why some massive galaxies stop producing many new stars and become dominated by older stellar populations. But the story is not one way. By compressing gas in some spots, an outflow can also trigger a short burst of star formation, so feedback can both kill and spark star formation depending on local conditions. There is a clear link between the size of the central black hole and properties of the galaxy around it, such as the mass and motion of stars in the central bulge. That relationship suggests galaxies and their black holes grow together. Feedback provides the physical handshake between them. Simulations of galaxy formation that include this kind of feedback reproduce many features of real galaxy populations, while models without it tend to overproduce stars and make galaxies that are too massive and blue. In short, feedback is the regulatory system that keeps galaxies from turning all their gas into stars too quickly. Think of the black hole as a sometimes grumpy landlord who heats the building when tenants get noisy. It's an imperfect metaphor, but helpful. The landlord can quiet things down by cranking up the heat, preventing new visitors, or accidentally start a small commotion that attracts attention, brief bursts of star formation. Astronomers keep improving observations across radio, optical, infrared, and 10th-ray bands to read this interplay more clearly, because understanding feedback is key to explaining why galaxies look the way they do today. Primordial black holes and dark matter hypotheses. Some scientists think tiny black holes formed in the universe's earliest moments could still be drifting through space today. These objects would not be born from collapsing stars the way familiar black holes are. Instead, they could have come from dense patches in the hot, young cosmos that collapsed under their own weight. In plain language, if the early universe had regions denser than their surroundings, those spots could have pinched off into compact lumps of gravity. Picture a cake batter with a few lumps that bake into denser berries, only much more extreme and with far less sugar. A key reason people take these primordial black holes seriously is that they behave like dark matter in an important way. They exert gravity but don't shine. Dark matter is the name given to the invisible stuff that holds galaxies together, and a black hole that doesn't give off much light looks right for the job. Think of them as invisible marbles rolling through a fish tank. You can see how they move things around without ever seeing the marbles themselves. That simplicity makes the idea attractive, because it means you don't have to invent a new particle to explain dark matter, you just use gravity and relics from early times. Testing this idea relies on clever, indirect tricks, because you can't point a normal telescope at something that emits no light. One method watches for microlensing, where a compact object briefly magnifies the light of a star behind it. It's like a tiny, wandering magnifying glass sweeping across a flashlight beam, the star appears to flicker or brighten for a short spell. Surveys that monitor millions of stars look for those flickers. Another method listens for gravitational waves, the ripples in spacetime produced when two black holes smash together. Those ripples are like the splashes on a pond when two stones collide, and detectors can pick up the pattern. If many of the merging black holes have properties that don't match what we expect from dead stars, that could point toward a primordial origin. A different angle checks the glow left over from the very early universe. If primordial black holes were gobbling gas, that would warm surrounding material and leave subtle fingerprints. Combined, these approaches have closed off many of the simplest possibilities where primordial black holes would make up all of dark matter, but they haven't ruled out every possibility. Searches continue, and the scientific picture is nuanced. Current evidence suggests that primordial black holes are unlikely to account for all of dark matter, though they could still exist as a fraction of it or in particular mass ranges that are harder to probe. Finding one would be a big deal even if it explained only a sliver of the dark matter mystery. It would open a direct window into the physics of the infant universe. In everyday terms, discovering a primordial black hole would be like pulling a vintage coin from an ancient pocket, unexpectedly informative and oddly satisfying. Researchers are using expanding sky surveys, gravitational wave observatories, and refined models to chase down remaining possibilities, because even a small population of these black holes would change how we think about cosmic origins and the hidden mass around galaxies. Micro black holes and particle colliders, reality check. Particle colliders slam tiny particles together at speeds close to light to probe the smallest building blocks of nature, and some theoretical ideas once suggested that under very special conditions those collisions might briefly concentrate enough energy in a tiny region to form a microscopic black hole. A micro black hole would be an extremely small pocket of gravity, far smaller than an atom, not a cosmic vacuum cleaner. The leading prediction from theory is that such an object would evaporate almost instantly by emitting particles in a process often called Hawking radiation, a way for black holes to lose energy and disappear. This means that if a collider ever did make one, it would behave more like a tiny, short-lived spark than a growing monster. It would be like a soap bubble that pops the moment it forms, visible for a flash and then gone. Experimental searches have been straightforward in principle. Physicists look for a burst of many particles coming out of a single point, a kind of miniature fireworks show in the detector. Detectors at large colliders are designed to catch exactly that kind of signal, and so far they haven't seen anything that lines up with a micro black hole. That lack of evidence places limits on how likely such production could be, without proving everything impossible. Cosmic rays provide an extra safety check. High-energy particles from space hit Earth and other bodies constantly with energies that can exceed those achievable in human-made colliders, and nothing catastrophic has resulted from that natural particle bombardment. If stable, dangerous micro-black holes were easy to make, they would already have left signs on planets and stars, which we do not observe. Some proposals tried to get around the huge energy barrier by invoking extra dimensions hidden from everyday life. In those scenarios, the effective energy needed to make a micro black hole could be lower. Think of it like folding a map. If space has hidden folds, shortcuts might exist that change how gravity behaves at very short distances. But experiments that test gravity and look for other telltale effects of extra dimensions have not found convincing signs, which pushes those ideas into tighter corners. In plain terms, it's like claiming there's a secret room in your house. The more you search, the more you notice that the furniture doesn't line up with that claim. Practical takeaway: the combination of theory and multiple experimental checks makes it extremely unlikely that colliders could create a dangerous, long-lived micro-black hole. If one were created, current understanding says it would vanish almost immediately and be harmless. Scientists keep searching because the possibility would teach us something profound about nature, not because there's a real risk. So you can keep your teacup safe. Particle physics experiments are exploring the tiny and the strange, not opening portals to sci-fi doom. Black holes in the laboratory, analog experiments. Laboratory analogs reproduce key wave behaviors of black holes by creating regions where waves cannot get away from a moving medium. In these setups, a horizon is not made of crushed stars but of a place where the flow of something, water, light, or sound, moves faster than the waves that try to travel through it. A simple picture is a fast current in a river. If the water speed past a point exceeds the speed at which surface ripples travel upstream, those ripples are carried downstream and cannot return. That is the same kind of trapping behavior physicists call a horizon, and it's the ingredient needed to mimic some black hole effects in a lab. Different experimental platforms make these horizons in different ways. Tanks of flowing water can be shaped so that surface waves are blocked at a visible boundary, letting people actually watch wave behavior that is mathematically similar to what happens near a black hole. Cold clouds of atoms known as Bose-Einstein condensates create a medium where sound moves very slowly, so it's easier to make a region where the flow outruns sound. Researchers then listen for tiny quantum-like excitations that behave like Hawking radiation in the analogy. Trickier approaches use light, short, intense laser pulses inside optical fibers or glass change the local speed of light inside the material, acting like a moving barrier for other light waves and producing effects that mirror trapped light. Each platform has its own strengths. Water tanks are visual and robust. Atomic gases are very sensitive to quantum behavior. Optical systems are fast and compact. Researchers look for specific signatures that show the analogy is real. One clear sign is the creation of paired excitations, one trapped on the inside of the horizon and one escaping, which can show correlations, like two dancers moving in step. Another sign is a spectrum that looks thermal, meaning the energy distribution of the emitted excitations follows a predictable, bell-like shape tied to the horizon's properties. Detecting these signals is not easy, because they are usually tiny compared with background noise. It's a bit like trying to hear a whisper in a busy cafe. Careful filtering, repeated runs, and clever measurement tricks are required to separate the subtle quantum-like emissions from loud classical disturbances. These experiments are practical in purpose and informative in limits. They do not create real gravity wells or singularities, instead they test how waves and quantum fields behave near horizons, helping to check mathematical ideas and suggest where our theories might need refining. Practical benefits include new measurement techniques and technologies for controlling waves in fluids and optics, sometimes inspiring engineering ideas for sensors or waveguides. And there is an educational payoff. A tabletop setup that demonstrates horizon physics gives students a visceral sense of abstract ideas. No need to worry, these lab black holes will not swallow your sandwich, but they do offer a safe, clever window into some of the strangest behavior predicted around true black holes. Myths, misconceptions, and common confusions. Black holes are not cosmic vacuum cleaners roaming the universe and gobbling up everything in sight. They are simply regions where gravity is so strong that, past a certain invisible boundary called the event horizon, nothing can get out, not even light. That boundary behaves a bit like the edge of a cliff. From a distance you can orbit it like any other mass, but cross the edge and escaping becomes impossible. People often picture black holes as hungry monsters that pull in nearby stars like snacks, but gravity doesn't work like a pair of cosmic lips. If the Sun were suddenly replaced by an object with the same mass but much smaller size, Earth's orbit would stay the same. We would just be in trouble because sunlight would disappear. In everyday terms, being near a black hole is determined by how close you are and how massive the hole is, just like the strength of a magnet depends on how close and how strong it is. The dramatic idea that you get stretched into a long noodle the moment you approach is partly true, and partly exaggerated. Tidal forces, differences in gravity between your feet and head, can stretch you, a process jokes call spaghettification. For small black holes those forces are deadly well before you reach the horizon. For supermassive black holes, the horizon can be gentle, you might cross it without feeling anything dramatic because the tidal differences there are small. There is no hard surface to land on. The center is a place where our current physics breaks down and can't describe conditions reliably. Black holes aren't completely invisible, contrary to the sci-fi trope that they are perfect black holes in the literal sense. Matter falling toward a black hole often forms a fast-spinning disk that gets very hot and shines brightly in 10th rays and visible light. Those bright disks can outshine the rest of their galaxy, acting like cosmic lighthouses called quasars. We also observe mergers of black holes by catching ripples in space itself, proof that black holes collide and merge, leaving observable signals behind. Some pop culture ideas claim black holes are shortcuts to other universes or time machines. Those are speculative fantasies more at home in movies than in current science. Wormholes and traversable shortcuts require exotic conditions and materials we do not have evidence for, so they remain hypothetical. Also, there's a long-standing confusion about whether information that falls into a black hole is lost forever. Physicists disagree on details and are actively studying ways that information might be preserved, though there's no settled answer yet. For everyday life, black holes are not something to worry about. They are far away and affect their surroundings in ways we can measure and study, helping us learn about gravity and extreme physics. So you can laugh at the wild headlines and remember, most myths come from confusing dramatic imagery with how gravity actually behaves, and reality is often stranger but also less hungry. Black holes in culture and science fiction. Authors and filmmakers use black holes as dramatic shortcuts to show danger, mystery, and the limits of human knowledge. On screen they often act like cosmic vacuum cleaners that swallow ships whole. In stories they become symbols for the unknown, a blank space that tests characters' courage. A black hole, in plain terms, is a place in space where gravity is so strong that nothing, not even light, can get back out. Think of it like a drain in a sink. Water spirals down, and once it passes the lip it's gone from sight. That simple image helps writers make the abstract idea feel tangible. Storytellers also use black holes to play with time and fate. Science fiction frequently treats them as shortcuts or bridges to other parts of the universe, the idea of a tunnel or wormhole that connects distant places. Films consult real scientists to make those ideas feel plausible. For example, a well-known movie worked with a physicist to show how time can slow near a very heavy object, a point that becomes a key plot twist. Other works prefer horror, turning a ship's encounter into psychological terror when crew members encounter strange forces they don't understand. In books and TV, the black hole becomes a mirror for characters' inner voids, too, a metaphor for loss, obsession, or the feeling of being pulled under. Visuals in fiction range from gloriously accurate to utterly flamboyant, and the differences tell us something about storytelling. Many movies show a bright, swirling ring around a dark center, which is based on the idea of hot gas and dust circling something massive. Artists then dial up the color and motion for spectacle. Sound is a different story. Space is silent in reality, so the booming rumble that accompanies cinematic black holes is a storytelling choice, not a physics fact. Everyday things help people grasp these images: a whirlpool in a bathtub, the way leaves spiral into a storm drain, or the pattern a mixing spoon makes in coffee, all handy analogies used by creators to explain what would otherwise be invisible and abstract. Language and culture picked up the black hole as a metaphor quickly. People say, black hole of debt, or black hole of bureaucracy, to describe something that swallows time, money, or paperwork. Musicians and writers borrow the image too. A popular rock song uses the phrase as a mysterious refrain, and a graphic novel uses the idea to explore teenage alienation, turning the cosmic into the intimate. Video games and TV shows recycle the trope as both hazard and plot device. Sometimes it's an impassable danger, sometimes a portal for travel, sometimes a MacGuffin that forces characters to act. These uses keep the idea alive in public imagination and inspire curiosity, even if the science is often simplified. Humor and everyday comparisons keep the concept relatable. People joke about their overflowing email inbox being a personal black hole, or about socks vanishing into the laundry as if a tiny cosmic drain lives in the washing machine. That kind of light touch helps stories connect. A terrifying, universe-devouring object becomes a versatile tool for comedy, tragedy, or wonder. At the same time, when creators bring in real scientists, the result can be surprisingly educational. Movies that aimed for realism sparked conversations about real physics in classrooms and online forums, turning spectacle into a gateway for learning. Current missions and future observatories. Several telescopes and detector networks are actively hunting signs of black holes across the sky, each using a different way to see what these invisible objects do to their surroundings. The Event Horizon Telescope links radio dishes around the world into one giant virtual dish to capture the shadow a black hole casts against bright gas. Think of it as stitching together lots of smartphone pictures to make a single panoramic photo that shows a tiny silhouette. Gravitational wave observatories like LIGO, Virgo, and CAGRA listen for ripples in the fabric of space, waves produced when black holes smash together, and have detected many such collisions, proving that merging black holes are not just a theory but a regular cosmic event. Space telescopes that catch 10th rays and gamma rays, such as Chandra, XMM Newton, NuSTAR, SWIFT, and Fermi, watch the hot, energetic light from gas being heated near a black hole. Their views are like infrared goggles for firefighters, revealing processes invisible to normal eyes. Meanwhile, instruments on the International Space Station, like NICER, measure rapid flickers in 10th rays from materials swirling toward compact objects, a useful way to study conditions very close to a black hole where things change on human timescales, blinking, but much faster than a traffic light. Planned and proposed observatories aim to widen the net and sharpen the picture, not just add more telescopes. A space-based gravitational wave detector will listen for lower-pitched ripples that ground instruments cannot hear, opening up the chance to observe the slow dance and final embrace of truly massive black holes. This is equivalent to putting a microphone in a new room to catch a whole different choir. The next-generation Event Horizon Telescope concept will add more dishes and new frequencies to the network, with the goal of making time-resolved movies of how the gas and magnetic fields evolve near the edge of a black hole, short clips instead of single selfies. Large 10th ray missions in the works are designed to dissect the light from hot gas with much finer detail, revealing the motions, temperatures, and chemical fingerprints of matter as it falls in or gets flung out, picture switching from a grainy weather radar to a high-definition Doppler map. Future ground-based gravitational wave facilities promise leaps in sensitivity. They will be like moving from a modest pair of headphones to a concert hall sound system for spacetime vibrations. Combining these various tools creates a fuller, more practical perspective on black holes and their role in galaxies. When gravitational wave detectors announce a merger, telescopes across the spectrum rush to look for any light that might follow, and that coordination can reveal jets, flares, or changing accretion flows, the swirling matter near a black hole, much as watching both the sound and the video of a band gives a better sense of the performance. This multi-sensor approach is often called multi-messenger astronomy, and it is already changing how scientists confirm theories and build models. Results from different instruments can be cross-checked, which reduces guesswork and sharpens conclusions. Everyday analogies help. Using radio, 10th ray, and visible light observatories together is like using binoculars, a thermometer, and a stethoscope at once to diagnose a patient. Each tool contributes unique, essential information. Practical benefits flow from the technologies and techniques developed for these missions, too. Algorithms for combining signals from many telescopes have improved image processing methods that can be adapted for medical scans or Earth observation. Precise timing and vibration isolation methods needed for gravitational wave detectors push engineering forward in areas like seismic monitoring and precision measurement. And on a lighter note, watching a network of instruments coordinate to study a black hole can feel a bit like an elaborate cooking show where everyone has a different kitchen tool. The result is better than any single gadget could produce. Overall, ongoing missions and the observatories planned for the near future promise to turn more mysteries into observable phenomena, filling in the picture of how black holes influence their cosmic neighborhoods while also spurring useful technologies back here on Earth. Open questions and where the field is headed. The heart of the mystery is that our two best theories of nature disagree about what happens to information that falls into a black hole. General relativity, which describes gravity as the bending of space and time, says a collapsing star makes a region from which nothing can escape and predicts a singularity where the laws we use today break down. Quantum physics, which governs the tiny world of atoms and particles, insists information is never truly destroyed. The clash leads to a real puzzle. If black holes seem to erase details about the stuff they swallow, then something important in our picture of the universe is missing. Think of it like watching a blender pulverize a photograph. You know the pieces are still there somehow, but you no longer know what the original picture looked like unless you have a way to read the chaos. One concrete strand of that puzzle comes from the idea that black holes aren't perfectly black after all. They slowly leak energy in the form of very faint radiation. This leak, predicted by combining quantum ideas with gravity, suggests black holes can shrink and eventually vanish. If that happens, where do the details about everything that fell and go? Is the information encoded very subtly in the outgoing radiation, or is something else going on? Scientists have proposed several answers. One popular thought is that the information is stored on the surface that hides the black hole, called the event horizon, much like a hologram carries a three-dimensional image on a flat plate. Another, more dramatic proposal suggests a violent barrier forms at the horizon that would fry anything falling in, a notion with the tongue-in-cheek name, firewall. A third idea says tiny leftover objects might survive after evaporation and keep the information. No single idea has convinced everyone, so the debate continues. To use a household image, it's like arguing whether the data from a corrupted hard drive can be pulled back from the cloud, recovered from tiny fragments on the disk, or is simply gone forever. Observations are opening new routes to answers, and they often behave like ordinary detective work, but on a cosmic scale. Telescopes that image the regions around black holes can map the shadow a black hole casts against glowing gas, revealing mass and spin. Instruments that sense ripples in spacetime, gravitational waves, let us hear black hole collisions and learn about their masses and how they merge. Combining these signals with light and particle detectors creates a multi-tool approach. Listening and watching at once gives a much fuller story. There are still big puzzles here, such as how the largest black holes grew to enormous sizes and how common exotic mergers are. Picture it like trying to reconstruct a recipe. One friend brings the taste, another brings the smell, and you need both to know what was cooked. The theoretical side is moving too, with people trying to build a consistent theory that treats gravity and quantum effects on equal footing. This work is like trying to stitch two very different fabrics together, one smooth and continuous, the other made of discrete threads. Proposals range from the idea that spacetime has a hidden quantum fabric to frameworks that reinterpret gravity in terms of information flow. Lab experiments that mimic black hole behavior, using fluids, ultra-cold atoms, or light in special setups, are proving surprisingly useful. They let researchers test some ideas in controlled conditions, even if they are only analogs of real black holes. Computers also play a huge role. Large simulations of colliding black holes and quantum models help predict what observers should look for, and even quantum computers may someday simulate aspects of black hole information processing better than classical machines. Practical progress will come from many directions at once: sharper imaging, more sensitive gravitational wave observatories, clever laboratory tests, and deeper theoretical work about quantum gravity and information. Directly detecting the faint quantum radiation from an astrophysical black hole is extremely unlikely with current technology because that glow is drowned out by other sources, but indirect tests and analog experiments are realistic and informative. Cross-disciplinary collaboration is essential. Astronomers, particle physicists, information theorists, and condensed matter experimentalists all have pieces of the puzzle. In the end, solving these questions won't just satisfy curiosity about extreme objects, it could reshape our understanding of space, time, and information, and maybe teach engineers new tricks for handling data, though a black hole hard drive is probably still a lousy idea. In short, a black hole is a place where gravity gets so strong that not even light can escape. Think of it like a waterfall in space, and once you pass the edge, there's no swimming back. We can't see black holes directly, but we spot them by watching how stars and gas dance around them, and by listening for the tiny ripples they make in space when they merge. They can grow by swallowing nearby matter, but they're not hungry vacuum cleaners roaming the galaxy. If the Sun turned into a black hole with the same mass, Earth would still orbit like before. Some theories say they slowly lose energy over unimaginably long times, like a candle that takes forever to burn out. The big ideas are simple: extreme gravity, a point of no return, and clever ways astronomers detect their presence. If this sparked your curiosity, you're not alone. First got chills the first time first pictured that invisible waterfall, and first'd love to hear what surprised you most. If you enjoyed the video, please like and subscribe so you don't miss future deep dives. Leave a question or thought in the comments and first'll try to answer it. Next up we'll break down how scientists actually took the first picture of a black hole, what would really happen if you fell in, spoiler, it's stranger than science fiction, and whether wormholes are just sci-fi or a real idea. Thanks for watching, keep looking up, and stay curious.